Okay, we are live. We got blinkies. We got screen. We do not have pointer yet. What do you guys? Do you guys like the crosshairs? I could go. Okay, crosshairs is good. Okay, all right. Has anybody actually been watching these? No? Yes? Okay. Yeah. No, yeah. Okay. Good. Always curious. All right. So let's see. I'm gonna do this. This. Yeah, problems from last year's midterm. Definitely don't want to do that for you. Yes. Hold on just one second. Let me get myself ready for you. Homework is due today, and there are graded homeworks out. If you haven't picked up the homeworks, give me your other ones. Okay. So let's do the one thing, which is review. The midterm is going to be a week from today. It is going to be in Kresge, 327. I have a feeling we're going to have a vast cavernous room, so you guys are going to have like a 10-foot radius between each of you, which is good. All right. So this is reminding me when the first it was differential equations class, open book, open notes, open any book you wanted, and people came in with just carting stuff behind them. They had like 5 separate books. You know, the CRC Handbook of Mathematics that has like every known solved differential equation, and you know, people had photocopies of everything everywhere. Everyone sort of just sat down and kind of made this ring around them of all their stuff. It was like the little forts you used to build when you were about 8. Yeah. Yeah. Yeah, if you like. You can bring other books. They won't help, but you can. Huh? Yeah, you can bring that too. Oh yeah, no, I know, but that's okay. I mean, I'll have the Laplace transform table that's in the book photocopied on the exam as well, and it's not gonna, as I said, it's not gonna make a big difference, honest. You'll think it might, but it won't. In the end, doing partial fractions is the easy way to go, and it's pretty ridiculously easy to do. Okay. All right. Homework 5. Probably you guys haven't looked at it yet because you guys are still looking at homework 4, which is due today. But it's out. It's all about root loci, and just doing more and more and more of them, and do them by hand, learn how to do them, and then bring them up to MATLAB to verify that you did them right. All right. This is sort of the way it works. You do them by hand. Don't do them by MATLAB first, and then do them by hand because you won't learn diddly, and then you'll flub the test, and then I'll have to fail you, and then nobody's happy. So, all right. And the review session, as we said, is E2 399, 6 p.m. The night before, and I'll be going over the practice midterm plus any other questions you guys might have.
And the homework is due Wednesday.
And the homework is due Wednesday at the start of the review, and I will post the homework solution right at the start of the review as well, so you guys can see exactly what that looks like. And any of you taken a look at the solution sets, by the way, that I've been posting? Yeah. Okay, good. So I'm just like, you posted solution sets? What? I didn't know about this. Nobody told me. Look on the website. Okay. Also, you guys know the trick about going directly to the. Sometimes I don't post a link to the videos immediately. However, you can always go straight into the directory, and it will automatically generate a list of all the files in it. It's a little different this year than it was last year. And the reason is I'm actually tracking the hits, so I can I'm aggregating statistics, and I want to see who comes in straight for the videos and who actually stops on the front page. And so far, there's someone in Turkey that's following this class quite well. So if you're out there, send me an email. Let me know who you are. Yeah, no, it's really funny because I have like the map of where they're all coming from, and there's like Turkey shows up. I'm like, how'd you find me? I don't know, but anyway. A couple of years ago, we had a guy from Algeria take down the SOE server because he was downloading the videos. For some reason, I guess it was the program he was using. It spawned like 1,000 threads to each download all the videos simultaneously, and it just overwhelmed it. And I got this panicked email from the SOE server guys, and they're like, "Who the hell do you know in Algeria?" And I'm like, "I have no idea. Why?" They're like, "Someone's taken down our server." So they eventually blocked it. But anyway, okay. All right. So we have questions. Ask away.
So I was wondering, The book mentions that there's, we talked about steady state error, S times E of S.
Right.
The book called it, they instead write it as the limit as S goes to 0 of just E of S. I'm wondering if that's just a typo.
No, the limit as S goes to 0 of E of S, right?
Yeah.
Okay, but that's E of S with what kind of input, right? So basically, the final value theorem, right, says that anything, let's call it W. So we've got W of infinity, all right, is going to equal to the limit as S goes to 0 of S, big W of S. This is the final value theorem. Okay? So, now, if I want to know, so I have epsilon of infinity is going to be the limit of S, limit as S goes to 0 of S, big epsilon of S. Okay? But be careful with this, because usually we don't give you what epsilon of S is. We usually give you, or you wind up calculating, what epsilon over R of S is. All right? So, well, what epsilon of S is, epsilon of S, right, let's say you calculate this as equal to some function of S, let's call it H of S. Right? So, epsilon of S is equal to H of S times R of S. Right? So all they've done here is they've assumed that R is a step. So if you put R as a step, it's 1 over S, right? And that's the S, and those cancel. That's all they've done.
So that's just assuming that.
They've just assumed, if you probably look carefully, they probably actually mention that it's the steady state error to a step input.
Well, because on the next, they define E as 1 over 1 plus L times R.
Mm-hmm.
And then on the next step, they just throw in that S without
right.
saying anything. And so I was
yeah.
a little confused as to where that.
Okay, so there it is. And yeah, you can also, by the way, since I have the, so generally I have my R goes in, my epsilon here, I've got some K, some G, here's my Y with a feedback, right? I can calculate E directly, but I can also say, hey, my epsilon, right, is actually equal to Y minus R, right?
R minus Y.
R minus Y, sorry. R minus Y. So epsilon over R is that. So I can say that, well, epsilon over R is equal to 1 minus Y over R.
And then you just use transfer function.
Yeah. Just transfer function, shove it in there, and put a 1 in there, it all works out. And by the way, since Y over R is equal to GK over 1 plus GK, right? So 1 minus GK over 1 plus GK is going to equal to 1 over 1 plus GK, which is exactly as we showed. So it all works out. Any other questions?
And then they also use the term loop gain.
Yeah.
That's just the multiple.
Go all the way around the loop. Multiply everything you see. All right? That's the loop gain. Okay. So the forward gain, all right? So often they call this the forward gain, all right? Is just going straight through from the input to the output, and then the loop gain is all the way around the loop. All right? That gets different if you've got something, a sensor that has dynamics in the bottom of it. Okay.
I have a question.
Yeah.
Is there a difference between determining an error constant versus steady state error?
Yes. So if you remember, the error constants, I don't like them particularly, but we had that KP says that, so for a type 0 system, then the error in steady state is going to be 1 over 1 plus KP. Okay? For a type, so this is position error, right? And it's 1 over 1 plus the position error constant. All right? It turns out that it's also, for a simple system, turns out to be what your proportional gain is, so it works in this case. But KV, for a type 1 system, then your steady state error is going to be 1 over kV. This is why I hate this, right? Because it's 1 over 1 plus kp for the type 0, but it's 1 over kV for a type 1. It's not consistent. And for a type 2, Ka, all right, so position, velocity, acceleration, right? X dot, X double dot. They're consistent in their numerology. And this is a type 2 system, and the steady state error is going to be 1 over Ka. And for a type N system, then the steady state error is going to be 1 over Kn for whatever they have. And they only call out the first 3. All right. So that's that. And again, I don't like this terminology because the type 1, the type 2, and the type 3, it depends on which input to which output, right? And so yeah, that's fine if you're just talking about command to output. But if you're talking about noise to output, if you're talking about disturbance to output, it changes. And so you can have something that's a type 1 system with respect to a command, but a type 0 system with respect to a disturbance input. And I find that terminology useless. On the other hand, it's used all the time in the field, and if you don't know it, you look like an idiot, so you gotta...
So if we ran the limit, the fundamental theorem with the limit and everything,
right,
and we got an ESS in that form,
yeah,
then we would root out KT and KV. Right?
Exactly.
So system error, does that just mean you always do it with the E over R?
Yeah, so your system error tells you what is your error to your command.
And this
right.
is a percentage.
Yeah.
Okay.
Yeah. So this is your steady state error. Right. So this is your steady state error, and what you can see is for a single pole system. All right. There's my single pole system. All right. So this, by the way, looks like something that has a low pass filter. All right. So this rolls off, and the frequency it breaks at is A. That's A. Or it's minus A rather. All right. Now this is a 1 over S plus A. There's my plant. I haven't drawn a plant in a while. Let's draw a plant. I miss my plant. Today it's a Seguro. Okay. There's my plant. Actually, I don't like that Seguro. Too symmetric. Okay. I still don't like that one either. But anyway, we'll live with it. Okay. So if I take this and I put it in a feedback loop, so I have some command. I'm going to put a straight gain K. I'm going to put my cactus over here, measure my output, and feed this back in typical negative feedback. I've got that. So the root locus now, as you guys should know, is pretty trivial. Right? So what's the root locus? There it goes. Okay, it's got one asymptote. There's the center of the asymptote. Doesn't really matter. The angle is 180. On the real axis is going out. So this one is just heading off to negative infinity. It's got 1, 0 at negative infinity. That's it. That's all there is. Right. So I can stop it at any point here, right? And the gain is simply going to be 1 over that distance. All right? That's the gain. All right? So I can make this thing arbitrarily fast. Right? Crank up more gain, get it faster and faster. Right? Now, what happens is, let's take a look at, so my Y over R, right, in this case is going to be equal to K over S plus A over 1 plus K over S plus A is going to equal to K over S plus A plus K. Okay, so there's my Y over R, and then my epsilon over R is just going to be 1 minus Y over R, right, which is just going to be equal to S plus A plus K minus K all over S plus A plus K, or this is going to be equal to S plus A over S plus A plus K. All right? Did I do that right? Yes? Everyone happy with that? Okay. So, here is my error, and I want to find what this error is in steady state. So I want to take, now, let's say I'm going to put a step input here. All right? So my error in steady state to a step is going to equal to the limit as s goes to 0 of s plus a, s plus a plus k times 1 over s. Right? So 1 over s comes from the step. This comes from the final value theorem, and that's my transfer function. Right? So I'm going to kill that, substitute in 0, and I'm going to get that this is a over a plus k. All right? Now, just for giggles, let me divide out by a, and I'm going to say this is going to be equal to 1 over 1 plus k over a. Okay? Suspiciously, that looks a whole lot like that. Okay? So I can speed up my system. How fast can I speed up my system? That fast. All right? How much error am I going to see in a steady state? Well, if I can take k all the way to infinity, then I get no error. Right? As this gets bigger and bigger, this number gets smaller and smaller. But it never goes to 0. I'm always going to have a steady state error. All right? How do I get rid of the steady state error? What do I add? I want to kill all steady state error. A what at the origin? I hear a 0. Do I get a second on that 0? A pole at the origin. Thank you. All right? I add a pole at the origin, which gives me an integrator. Okay? Now, what happens to the root locus as I crank this gain up? All right, well, I get something in between. Right? These take off. I have an asymptote. It's going to be right in between there. I got 2. Which way are they going? Plus or minus 90, right? Up and down. Okay? So now I say, hey, no problem. Arbitrarily pick a spot that's got some nice damping. Right? 45 degrees gives me 5% overshoot. Happy with that. All right? This is a zeta 0.707. By the way, an optimal control, whenever you run all the optimal control methods, which are they go by funny names. So there's the LQR control for linear quadratic regulator, LQE, linear quadratic estimator, LQG, the linear quadratic Gaussian, when you take both of these and you combine them together to make that one. All right, so the estimator says, I've got all these unknown states in the middle, but I have some measured output. I want to estimate those states based on the output in my assumed dynamics. LQR says, I measure all the states. I've got a measurement of every state in the system, and I want to drive this thing, to, basically to 0. It's a regulator, right? And you can make a track command, but it's if you can measure every state in the system, the control you get is phenomenally good, and by the way, has 0.707 damping on every mode. All right, it will bring it in with 5% overshoot in minimum time. So, anyway. Not that you guys need to know that. Hopefully, we will actually get to a little state space at the end, and that'll be kind of cool. All right. So now I say, hey, I can pick the k. Right. The k that's going to get me this is 1 over both of these lengths. Right. So this is L1, L2. K is going to equal to 1 over L1, L2. All right. And so I have my k that puts me there, and now I can either, I can go ahead and solve this. All right, and say, well, what is this? This is 1 over s plus a. All right, and I'm going to put it in a feedback loop. I'm just going to put a k on top of it, run it in a feedback loop. So my error, right, is going to be equal to 1 over 1 plus k s plus a, which is going to equal to s plus a over 1, I got s squared plus sa plus k, or I guess as. All right, so there's my transfer function. I want to take the limit as s goes to 0, put an s up here, 1 over s there for my step. Okay, and now, I kill one of them. Hey, look at that. 0. This goes to 0. All right. This will have no steady state error, period. It can't, because this thing is integrating. All right. So whatever error you have, regardless of where you generate it, that one's going to integrate it out. All right. Guaranteed. All right. And generally you put a very, very small gain on that because you don't want it going awfully fast. But, in this case, yeah, add integral control. Done. So integral control has some very nice properties. It also has some very dangerous properties. Right? It's easy to throw it on there because it winds up killing all of your steady state error. And so generally what you do is you tune for performance, right? Once everything is performing nicely, right? And let me remind everybody that when we do, well, this is just, that's square root of, so omega n is going to be square root of k, and zeta is going to be a over 2 square root of k. These only work for a second order system. Right? For a second order system, the approximations are exact. All right? When it's not a second order system, then the approximation is no longer exact. Okay? It gives you sort of a first cut of where you're going. So the idea is you use these to get your first cut. You design, you simulate, you take a look. Is it, if you can, you experiment on the real system. If it works, great, you're done. If it doesn't, you go back and you tweak it a little bit more. It's an iterative process. You go through and you keep doing this over and over again. Okay. So we were at last time we were doing the last rule, which is the break-in and the breakouts. All right. So let's summarize our rules once again. So root locus rules. All right. So first one, x to O. 2, real axis, which is left of an odd number of thingies. 3, the asymptotes. Center of asymptotes, sum of the poles, sum of the zeros, divided by n minus m. And the angle is just, look at it as n poles at s minus alpha and figure out where they have to be to break out. That's the way I remember it. There's a formula. Use it if you prefer. 4, we've got departure angles. Again, put yourself right next to your pole. Okay, and draw yourself a little circle epsilon away, and you are on the departure angle on that because you're on the locus, and sum up the phase to all of the other ones and find out where it's 180. All right, and you'll solve for phi d. Same thing for phi arrival. You do the same thing, but now you do it around the 0. All right, so you're going to be, a little phi arrival away. All right, and you just solve it for 180. Again, the whole thing you'll notice all of this is just looking for the phase angle of 180. That's all we're doing. Okay. So those were the big ones. Now, where the locus crosses the j omega axis, it is unstable. This is one of those things where it's easy enough to just plug in j omega and search. Right? So I've got, something that looks like that. Let's do those two, this, and that. All right? So there it is. I just arbitrarily threw that down. By the way, that is a rather hairy polynomial to factor. All right? This is s cubed in the numerator, s cubed in the denominator. All right? And yet, I can say, hey, not only can I factor this, I can factor like where it goes in the feedback. All right? And, what does it do? Well, that one goes there. All right? These two are coming in, to depart, to arrive. All right? So they're all going somewhere. So where am I going to find this? Do my little phi d, and I've got what? 90 from that one, a little less than 90 from that one, and big one there. And I say, hey, you know what? Figure it all out, add it up to 180, and I'm probably departing somewhere around there. All right? I might not be, but wherever. It'll be symmetric. Do the same thing for this one. Figure out where it's going, and I'll find my my arrival angle. And again, it's going to be symmetric. And then I say, okay, connect the dots. All right? There they go in. That's the accuracy we want. Now, how do I find out at what gain it goes unstable? Well, I know that I'm going to find on the j omega axis a point at where the phase to all of these adds up to 180. Okay? It's a trigonometric solution. All right? I can look for it. I usually can get fairly close to where I need to be, all right, and start looking around there. If it's a simple trig function, I can do it. If it's this complicated, well, guess what? I'll probably use Rouse because that's the one that will get me there fastest for a limit on k. But if that doesn't work, fire up MATLAB, right, to get it. And then the last one we had was the breakaway points. So these are break-in or break-out points. And what we said was our n of s over d of s. We rewrite this as b of s over a of s. And basically we solve for b dA ds plus a dB ds equals 0. Okay. So now let's see if I can prove this to you. All right. So what was that? Oh, yeah. All right. So let's take a root locus. Here's a. I'm going to have 1, 2, 3, and 1 here. Okay. So let's draw the root locus. Okay. First step, real axis. Okay. Where is it? Between them, right? This one's leaving. That one's leaving. Okay. Interesting. Center of asymptotes. Where? All right, remember, I'm trying to position a fulcrum that's going to balance these guys. Quarter away from the cluster, right? There's my center of asymptotes. What are my asymptotes going to be? I got 4, right? Zoom way in the hell out there. I've got 4 poles right on top of here. What is they're going to be? I saw someone make the sign. Okay, the sign of the root locus. All right. So there it is. 45's off. All right. Departure angle. Okay. What is this? I got 3 poles on top of each other. What are the departure angles? Right. 3 slices, right? So this is going to be at 60, minus 60, and 1 going that way, which we already knew about. All right. So this one fares in, goes that way. This one fares in, goes that way. Now, the interesting one is that these two meet up somewhere and split. And where they split, they then go and join along. And by the way, they will split at 90 degrees. Right? They'll hit each other and they'll break off at 90 degrees and then go off that way. Okay, so we want to find out what this point is. So in this case, our plant looks like 1 over s cubed s plus a. Okay? Or I'm going to write it out long and multiply it out, and it's s to the 4th plus as cubed. Okay? So now, I've got that this is equal to, so b of s is equal to 1. dB ds is equal to 0. Generally, I can do these when I don't have something, and as soon as I have something in the numerator, it gets complicated. But, okay, a of s is equal to s to the 4th plus as cubed. dA ds is going to equal to 4s cubed plus 3as squared. Right? So, 4s cubed plus 3as squared equals 0. All right. Now, the first thing I can do is I can say, hey, I've got that s squared equals 0. Right? There are 2 breakaway points at s equals 0. Hey, I know where those are. Right? That's the origin. S equals 0. Hey, I knew that. Right? How did I know that? Well, because they're my departure angles. Right? I got 3 on top of each other, and yeah, they break away. Okay, so I got that. And the other one I have left, once I take that out, so I have s squared times 4s plus 3a equals 0. So I got the s squared equals 0. That means that 4s plus 3a equals 0, or that s is equal to minus 3/4 Is that right? Minus 3/4 A? Yeah. All right. So there's A. So it's 3/4 of the way out. So that's a quarter, half. So I got it a bit wrong. Right? There it is. Right? And voila. I have my breakout points. Now, let's see why this works. All right. So, all right. I've got my N of S over D of S is equal to B of S over A of S is equal to S to the N B1 S to the N minus 1 all the way down to B N S, Bn minus 1s Bn. So there's and that's why it's a B of S, by the way, because there are B's in the numerator. And there's A's in the denominator, so I have S to the M plus A1, S to the M minus 1, all the way down to A, M minus 1, S plus A, M. Yep. So far, done nothing. Okay, good. Now, I'm going to put this in my standard feedback form, and I'm going to say, look, I've got that 1 plus K B over A equals 0. And I know that my closed loop poles, right, are going to look like A of S plus K times B of S, and is going to equal to 0. Right? And now, what I'm going to do is something a little funky here, and I'm going to say that this equals to, whenever I have a repeated spot on this, remember, this is all of the possible locations, right, as a function of K, all the possible locations of the closed loop poles of the system. I'm going to say at some point, I'm going to have multiples that are right on top of each other. So I'm going to pull those out. At the point where I have a multiple, I'm going to call this as S minus R to the Q times F of S. Right? I figured out there's a K at which I've got multiple poles on top of each other. Right? That's the whole point of being a breakaway or a break out or a break in. All right? They're going to break out together, or they're going to come together, but when they do, they're going to be on top of that one point, and there's going to be multiples of them. And maybe I'll have, 2 of them most likely, but very often I can have, 4 or 8 of them coming together at one point and then going somewhere else.
Is that F, R, Q times then?
Yeah, it's so there are Q poles at R. Right? Is the idea here. Now, so this is the break-in or out point. Okay? And what I'm going to do is, at this point, I'm going to say, hey, DDS of that mess, right, is going to be Q times S minus R, Q minus 1, F of S, plus S minus R, Q, dFds. All I did was I just did the chain rule here. Right? All right, evaluated at S equals R. Right? And if I do that, well, this side, that goes to 0. So what I'm left with is Q times 0 to the Q minus 1, which I don't particularly care about, times f of r, or rather, what we got? We got q times 0 times f of s plus 0 to the q df ds. All right? Now, what I can then say is, well, what is my df ds? Df ds is nothing more than dds of as plus k b of s, all right, which is equal to dAds plus k dBds, and it equals 0. All right. So now I need to know what k to put in here. All right. So the k I'm going to use is to remember that I still have that 1 plus k b of s over a of s equals to 0. Right? Therefore, I can pull out that k is equal to minus a of s over b of s. Right? Yep. There you go. Shove this back in here. All right. And I get that df ds is equal to dAds plus a of s over b of s dBds. And this has to equal 0. Yeah, so that's a minus. Okay. And do a little cross multiplication, and I wind up with b dAds minus a dBds equals 0. And there it is. All right, so all we've done here is we figured out where the break-in and the breakout goes. Now let's do. Now let's see. This is.
Can you go back one slide?
Hold on. I think I. Okay.
There's a minus where there should have been.
There is a minus where there should be a plus. All right. Where is it?
It's in one of the S books.
Well, so the original was b dAds plus a dBds is what I have here.
Right. Yeah, and that's where we were supposed to get to. And I've got a sign error somewhere, and I can't quite figure out where I've got it. So hold on a second. I've got. I think we're okay up to here. I think it's up in here. All right. I've got dAds plus k dBds. Sorry, dAds plus k dBds, right? And then I've got that 1 plus that. That's going to be minus a somewhere. I wind up with a plus on this one, but I'm not quite sure where I got it. Right? Because here I have a minus, but I'm pretty sure it's supposed to be a plus. So I've got a negative sign somewhere. Oh, I know where it is. No.
On the second to last line there, you have s minus r to the q.
Yeah, that should be a.
When you plug the r in, that just goes to 0, and that's what was confusing.
Right, that goes to 0.
That goes to 0 as well?
Right, s minus r to the q goes to 0.
Okay. So then don't you just put 0? I don't see how.
Right, so you have,
0 plus.
0 plus 0,
Oh.
right?
Oh,
So you're finding the breakout point, right? So now you take the derivative of it, and you still have 0,
okay.
right? Because you have a multiplicity of it.
Okay.
All right. So this is plus, but I'm not quite sure how I screwed this up. And that. BDS a. All right. So that's that. Yeah. So somewhere this is supposed to be plus, but that's the right one. And the book has the book probably has it without the sign error, because I got it in my notes with the sign error, and apparently I did this consistently last year too. No one seems to have caught it last year as well, though. Anyway, in general, you're going to find that this only works when one of these is 0 anyway, in which case the negative sign doesn't matter a whole hell of a lot. But so it doesn't. It's not terrible. But let's take a look at an example of how we actually apply it. So we did the break-in for that. Let's look at one that's a little bit more interesting. All right. So I'm going to have 2 poles up here, and I'm going to have a 0 here. Okay. And I'm going to say, okay, let's find me a point. Okay, where this works. All right. So what I've got here is this is going to be, and I'm going to put everything at 1. So this is plus j, that's minus j, and this is at minus 1. Okay. It is minus? Oh. So I got it right. So that means way up here, and I had this written down, this is minus. So I did get it right. What's that? Yeah, there it is. So it should be a minus. Correct that in your notes. Right, that's a minus sign. And so the examples I wound up picking always had it with one of them 0, so it didn't, to make the factoring easy, so I never actually noticed. So yes, it is a minus. How about that? I actually got it right. I was wondering where the hell the plus sign came from. I was looking at my notes going, wait a minute, it can't be a plus. Anyway, all right. So here it is. So this is, for my plant, bad pot. Well, there's my plant. This one is going to be a s plus 1 in the numerator, that's that, and then an s squared plus 1 in the denominator. Those are those two. Okay? So, A, let's do B first. B is s plus 1, dB ds is equal to 1. A is s squared plus 1, dA ds is equal to 2s. Okay. So far, so good. As I said, it only works on a particularly easy one. So now we're going to do B dA ds minus A dB ds equals 0. Okay. So we've got s plus 1 times dA ds times 2s minus s squared plus 1 times dB ds, which is 1, equals 0. So I got 2s squared plus 2s minus s squared minus 1 equals 0. So that gives me s squared plus 2s minus 1 equals 0. Yeah? I go a long way with 8th grade algebra. I just want you guys to know this. All right? So now we're going to factor this, and what do we got? We got minus 2 plus or minus square root of, what is that? Minus 2 plus or minus, let's see, I got 4 plus 4 in here, all over 2, all right, which is equal to minus 1 plus or minus square root of 2. Okay, now, so first of all, note that this is real. That's important. All right, it's on the real axis. I get 2. Right? Why am I getting 2 here? There you go. Somebody's been reading ahead. Okay, so we know already that from the root locus, this is on the root locus. One of them is going here. One of them is going out to minus infinity. If I calculate the departure angle, very quickly I'm going to see that it is perpendicular to that ray, like that. Okay? And the answer is, where possibly do they meet up? And the geometric way of looking at this is if I extend this down here, that's one possible one. And if I take the circle out around here, that's the other possible one. All right? So one of these answers, right, is going to be for the negative feedback, the normal one we use, and the other one is going to be for positive feedback. So you have to actually check to see which one makes sense. Yeah. Oh, we're going to get there in about, 2 minutes. Huh? All right. All right, so what we've got here is we've got, roughly negative 1.7, right? And also we've got positive 0.3. All right, rough numbers here. So that's this one where these two come in like that, boink, boink from the positive feedback, right? And this over here is a bit more than, not, it's actually exactly sort of the radius away if you work it out. They come in and smack down in here. All right? What's that? Oh, you're right. That's 1.4, isn't it? So minus 1 minus 1.4 is approximately negative 2.4, and this would be approximately plus 0.4. Right? Better. Okay. So we've done that one. We can do, for giggles, do I want to do this one? I'll show you why it's kind of useless. This is why I'm not a huge fan of the break-in and breakout. I think for simple examples it works just fine. But now I have 1, 2, 3 at minus 1, and one more at minus 2. All right. Now we did the one before where these were at 0, and it worked out fine because a lot of that was 0. But now we're going to do this, and we're going to say, okay, here's the root loci. It's doing this. I know that I've got, here's going to be my center of asymptotes, 45 degrees. These two are going off at 60. That one's going in. They're going to split somewhere, and they're going to do something. Okay, now I'm going to find the point of that split. So in order to find the point of that split, I've got that g of s is going to be equal to 1 over s plus 1 cubed times s plus 2. All right, so b of s is equal to 1, db ds is equal to 0, so I'm happy with that. All right, so all I'm left with, however, I need to find a of s, right? And a of s, if I multiply it all out, s to the 4th plus 5s cubed plus 9s squared plus 7s plus 2. That part I can do, and I'll even imagine giving that to you, to do by hand. Right? The problem is, okay, so now I'm going to take the derivative of this, so I'm going to have 1 times dA ds, which is going to equal to 4s cubed plus 15s squared plus 18s plus 7. Factor that. All right? And that's the problem. All right? Now, by the way, I have an advantage. I know that one of the roots, in fact, I know that 2 of the roots are going to be at minus 1. All right? So knowing that, I can actually help me to find the third root, but it's still a pain in the butt. All right? And so it's not easy. Right? And since it's not easy, we don't do it. Right? So if you find yourself doing this, you've probably made an error somewhere, and ignore it. You can do little clever things, by the way, right? You say, well, the root locus is actually insensitive to translation, right? So I can say, hey, I know what I'm going to do. I'm just going to translate this over so these 3 line up on 0, all right? And then resolve it, and then just remember to shift it back. Right? Works just fine, by the way. But I wouldn't expect you to sort of figure out such a sneaky trick unless I'd actually mentioned it, or something like that. The recording actually on? That'd be a good thing to check. Yeah. Okay, that's fair game now. Okay, which brings us to the 0 angle root locus. So there are a couple of times in your life as an engineering as a controls engineer, where you will hit a problem where you say, okay, there might be a time when the using positive feedback is going to work. The way in which we generally, so here would be the typical drawing. So I have my reference. Instead of coming in with a minus, I'm going to come in with a plus. All right, and I've got my K, and I've got my N of S over D of S, and I come in with my feedback loop. Okay. In general, we don't write it this way, just because it confuses people, and most people will actually never even look to see whether there's a plus there. So what we do is we say, look, there's a negative of the absolute value of K in there. Okay? So I just move the minus sign into the gain. Right? So this is negative gain or positive feedback. All right? So when we talk about the zero angle, we're talking about the negative gain.
You still have like a difference between your output and your input.
Yeah.
Because R is negative 2 now.
Because now R has to be negative 2.
So you could put negative 1 gain before the summation section.
You could, right? You could do a, an amplifier of minus 1, like that, through. But, or you could just do this, right? And then it works. But the answer is, it's just you're talking about positive feedback, and very often, in the context of regulator, R is 0. So it doesn't matter whether it's positive or negative. So you're saying, hey, I want to bring this thing back to 0. So how do I do it? But what we're interested in is what effect does having this around. So if I look and I go through my feedback loop, I've got 1 over, now it used to be 1 plus kg, right? It's now going to be 1 plus my negative absolute value of K, N of S over D of S, right? Or, whereas what we used to, so what we want to wind up with is 1 minus Kn over D up here, right? So now, if we're, in other words, we're still assuming that K goes from 0 to positive infinity, all right, in our root locus when we draw it, but now we've got that negative sign in there instead of a positive sign. So if I look at the characteristic equation, I get 1 minus Kn over D is equal to 0, which means that Kn over D is equal now, instead of negative 1, positive 1. Right? Which means that the magnitude of Kn over D is still equal to 1. Right? But the angle is now equal to 0 degrees. Right? 0 degree root locus. Now, there are a couple of so this causes things to flip around in ways which are interesting. Right? If you use the rules the way I've taught them to you, very little changes. Okay? So let's go through. The first one still starts at the X's, still goes to the O's. All right? Hasn't changed at all. Now, this one is, if you can either do this, or you can do left of an even number is on the locus, and in this case, 0 is even. Or you can also do to the right of an odd number, all right, and go that way. That works as well. Yes. Right. So, well, it works the other way. Or you can say the other way. So you can also say this as to the, so this is the right of an odd number. Or you can say, give you one more way of saying this, which is not to the left of an odd number. All right. So in other words, You say, okay, I know how to do the left of an odd number, and then everywhere was blank is now covered, and everywhere that was covered is now blank. All right? So this is probably the hardest one to remember. All right? And if you get confused, just sit there and add up pick a point, add the phase up. It's on the real axis, so everything cancels out inside the 0, 180, and just add them all up, and you're done. Okay. The angle of first of all, the center of the asymptotes does not change. Okay, so this is the same. So the sum of the poles, sum of the zeros, divided by n minus m. Okay. The angle, all right, if you did the same thing we did before, where I say just zoom way out and consider that you've got, n minus m poles at alpha, right? Except that now instead of looking for 180 degrees, you're looking for 0 degrees, right? Before, everything we were talking about was looking for 180 degrees of phase. Now we're talking about only looking for 0 degrees of phase, right? So if you want the actual formula, instead of it being 180, it's now 0 plus L minus 1 times 360 degrees over n minus m. Again, for the asymptotes, for the departure angles, any arrival angles, everything is the same except that now you're looking for 0 degrees instead of 180. All right, and symmetry still works. So that's everywhere. And lastly, the break-in and the break-out is still A dBds minus B dAds equals 0. Okay? And remember, that one's useless. Okay. So let's take a look at the one we had before. Minus 1, minus 1, minus 1. All right? So we had for our 180 degree root locus, our normal one, that this is going there, these are coming here, and that's coming there. Okay? So there was our 180 degree root locus. Our 0 degree root locus is going to be this one going out to infinity, these two coming down here, intersecting and splitting. All right? So, in this particular case, right, using positive feedback just buys you instability. Right? Starts off oscillatory instability and then gets to just a very nice exponential growth away. Right? No fuss, no mess, just departure. There it goes. All right? So, in this case, it doesn't buy a whole lot. Right? So this is the 180 degree, and this is the 0 degree. All right? Now, so again, I can take a look at this and figure out, so here's a point right here on the locus. All right? To figure out that this is on the locus, I just say, well, okay, look, I got that angle and that angle. They cancel each other out, right? And I got 0 degrees from this 0, so I've got 0 degrees here. Right? Likewise, I can define the the array still is a challenge. Okay. If I want to find the departure angle, right, I'm going to make my little phi departure away. So I've got that minus phi departure. It's a pole. The phase is still negative. Okay. Minus 90 degrees. Right. There's that one. Plus 45 degrees. Now, instead of this equaling plus or minus 180, this equals 0. Right. Because I'm looking for the 0 angle root locus. Right. So phi d is equal to, well, it's going to be minus 45. So did I get that right? Minus 45 degrees? Yep. So, there it is, 45 down. There she goes. All right? Break in, as I said, when you do the break in and the break out, you'll find you always get two solutions. Right? One for the 0 angle, one for the 180. All right. Now, let's take a look at another one I've got here. Let's see, this is, oh, I'm just trying to see.
Get one solution that corresponds to them both being on the real and put together.
Right. Well, no. You'll get two solutions that come on the real axis from this one.
No, if both roots are on the real axis and they're coming together,
Yeah.
you only have one solution.
No, you have two. You're going to have a solution here, and you're going to have a solution here.
Right, because they'll split, orbit around, come back.
Right. So if they're always going to orbit around. For the 180, they're going to orbit this way and come down here, and for the 0, they're going to orbit that way and come down there. So these will hit faster. Right. You'll hit this solution first, and then you'll hit that one.
Yeah.
Right. But you will when you do this thing, the ADBDS minus BDADS, you're going to get two solutions. All right. I got one here which looks like 1, 2, 3. Funny. All right. Well, I've got a. I'm trying to see. All right. What do I have? Okay. So let's take a look at this one. I've got another one. I'm going to try something fancy here. Yes. I'm telling you, kindergarten got me through life. Look at that. Very nice. Huh? Yes. As you know, I'm very good at sharing. Okay. Let's say I've got 1, 2, 3. All right. So let's first do the 180 root locus. So the normal one we're used to, just to make sure we're good. Coming along. In between here. All right. Nothing, and this one's going off. All right. Center of asymptotes is going to be the balance point between this one. Let's say I'm going to make my life easy. 0, -1, -2. All right. So the center of asymptote is going to be right on top of that one. So alpha is just going to be -1, -2, -3 divided by 3 -1. Okay. So there it is. My angle, so I've got 1, 2, 3, right? I'm looking way out, trying to see what my angle of my asymptotes are, right? And I know those are plus 60, minus 60, and 180, right? Did I confuse anyone with that step? Jared, you're looking a little, I'm doing the normal, right now I'm doing the 180, okay? So from here, I've got a 60 degrees going up. Now, by the way, on this one, if I asked you at what gain does this go unstable, right? What you can say is, hey, the first approximation, there, right? It's going to get on the asymptote. It's going to be pretty close to it, right? So, whatever error I make though is going to be pretty damn small. Right? Now, I need to do a break in and a break out. All right. Well, I know these two are going to come together. They're going to split, and they're going to come out at 90 and do that and that. Now, the other thing is with this one, all right, if I actually wanted the j omega crossing, all right, I say, no, that's not good enough. I want the exact one. All right. So I want the exact point at which the gain at which this system goes unstable. All right. How am I going to do it? I can do it rough, but let's do it geometrically. All right. So I want it geometrically. I know that this is going to be omega, right? That's -1, and that distance is -2. Right? So I know that and they're all poles, right? So I know that this one is going to contribute 90, right? So I've got 90 degrees minus, right? I'm just going to stick them all as negative. Minus 90 degrees minus arctangent of omega, right? Omega over 1, minus arctan of omega over 2, right, is equal to minus 180. All right? And I say, hey, I can now solve that transcendental equation, kind of. In this case, it's a little hard, but, you know. Okay, so scrap the geometric method, all right? At that point, I'm just going to say, hey, 60 degrees up from minus 1, right? That's minus 1 times square root of 3. Is that right? Minus 1 over square root of 3 for the center. It's equilateral triangle, right? So it's 1, that would be 2, right? 1/2 base height, square root of 3, I think it's, is that right? 60-30 triangle? Yeah. We're almost in 7th grade here. Come on. Huh? Yeah, oh, come on. All right. Equilateral triangle, right? This is right. So this is 60, right? That's 1, so that's 2, right? So this is square root of 3, right? So there's that point, right? Square root of 3. Come on, you guys. Not helping me here. All right. Okay, so there it is. I've got that, and I can find my breakout points if I'm really so interested. All right, and fine. Okay. When I calculate the breakout points, by the way, I'm going to get 2 answers. Anybody know where the other answer is going to be? Shall we do it? Do you guys want to do it, or do you guys want to just sketch the 0 first, and then we'll go?
It's going to be like a halfway to the other side of that, where that gap is.
Right.
Rather than maybe 2 basically.
Yep. Okay. So for the 0 angle, right, I'm going to have, so anywhere I don't have on the real axis for the 180, I've got for the 0. So that means that and that. All right. The center of the asymptote's in the same place, except that now minus 3 phi a, instead of equaling 180, is now going to equal 0. All right. Which means, well, there's the one going that way, and it splits the circle, so that's going that way. And again, these two are going to meet and split and go off along the asymptotes that way. All right. So they're actually going to be, one of the interesting things is the 0 angle and the regular ones are pretty damn close to symmetric with each other, so there's often a mirror image, right, with some slight variation on it. But they're going to be pretty close. All right. Shall we, let's solve for the break-in and the breakout on this. So I've got G of S is equal to 1 over, I've got S plus 1, S plus 2. Right? So this is going to be S squared, S times S squared plus, what is it, 3S plus 2? Yep. Okay. So I've got S squared plus 3S plus 2 times S, so S cubed plus 3S squared plus 2S. All right, and I want DDS of that, all right, is going to equal to S squared plus 6S plus 2 equals to 0. 3S squared. Okay. Divide through by 3, and I've got the S squared plus 2S plus 2/3 equals to 0. And solve the roots of that. One of them is going to be there. The other one's going to be there. All right. Andre looking confused. No. Okay. Good. All right. So now let's take a look at another one that I've got. All right, for fun. So I'm just doing a bunch of these to try to get, what's that? Yeah.
So the pole at negative 2
Right.
comes into the point of like negative 1.
Right. For a zero angle, i.e., when I'm using positive feedback, all right, These two move towards each other as this one goes out into the right half plane. They hit and they split and they go up along the asymptotes, getting better. So again, the convention is the red is 180 degrees and the green is the 0 degrees. Yeah. Right? I'll just do just the 0 degree. So we had one. We had this. This is at 60. These split and go off this way, and this one goes off this way. Again, not particularly useful, right? Because as soon as I crank the gain up at all, I've got this one's unstable. It's going off. So this is the 0 degree root locus. All right. I got one. I got two. Let's see if this one gets interesting. All right. Now I'm going to make things a little more challenging. So I've got the 0 here, and I've got 1, 2, and 1, 2 there. Okay. So for this one, let's start conventionally with the 180. All right. So the 180. All right. That's on the locus. I've got 3 excess poles over zeros, which means I've got 3 asymptotes. The center is, so move that to the other side, and it's going to be where that balance is, so it's going to be right, basically it's going to be 1/3 the way to this one on the other side. All right, so 1, 2, right about there. That's the center of asymptotes. All right, and I've got 3 of them, which means that, right, that's 60, that's minus 60, there's the one that's at 180. All right. Now, departure angles. All right. Let's do this one. So again, this is at -1. These are at 0. All right. So I'm going to take right here, and I'm going to have my little piece on the locus. Right. And I'm going to have -2 phi d. Right. I'm going to have -180. Right, from these two. Plus 45 from this one, right, that's that angle, is going to equal to 180. Right, let's make it -180 since it doesn't matter whether I do plus or minus. Okay, and what I'm going to say is that phi d is going to equal to, so I'll start with the plus 180. So plus 180 minus, that's 360. 360 minus 45 is going to be, what the hell, let's do the minus 1 first because it makes the math easier. All right, here's the -180. All right, so -180, that goes to 0, so I've got phi d is going to be at -45, right? Divided by -2 is going to be at 22.5. Okay, there's the first one. All right, and then to solve the second one, I can just say, well, you know, add to it yet another. What's that? Right, 157.5, because they're gonna split the circle, right, to give you that way. So 22.5 is right about. So 22.5 is halfway to 45. That's about there, and then 180 degrees opposite is that one going there. Okay. So symmetry applies. Right. So for the now I can actually find the break-in points and the breakouts. Right. And what I'm going to discover, I'm going to get one root. It's going to be down here somewhere. Right. And these guys are going to go thunk like that. And these two are going to go out to there. So far, so good. What's that?
Second one would be just shy of 0 on the other side.
Ah. Where is the second root going to be? Okay. So now let's do the, so this is the 180. All right. Let's do it, same one, but now we're going to do the 0 angle. Here's my 0, 1, 2, 1, 2. Center of asymptotes remains unchanged. However, this time, right, this side is on here. Now, when I do this for my phi departure, right, I got minus 2 phi departure, minus 180 plus 45 is equal to 0, right? Which means my phi departure is equal to minus 67.5. All right, let me do one step in between there so you guys follow me. I've got 2 phi departure is equal to 135, and therefore phi departure is equal to minus 67.5. So that means that this now goes, so it's half of, so that means I've got, see, minus 67 is going to be right around there. There's minus 67.5, and the other one's going off in that direction. The asymptotes, remember, are now at, right, they're now 60 degrees up from here. Right? The 0 one is still there. Right? I'm still splitting the circle into 3. I just now know that one of those splits is going along this axis. Right? So this one, hey, that one's going there. These are symmetric. This one's coming out to here. And these two are coming down and meeting somewhere in there. Right? One of them goes back towards this guy, and one of them goes out towards that guy. Right? Now, where's a place where, so far, I haven't shown you anything where the zero angle actually buys you anything. Right? Every single time we've been having something going in the right half plane. In fact, this is a nice ugly problem. In fact, this is a good one to try to learn to stabilize. Right? Because simple gain won't get you there. Right? Let's digress before I hit the next one and see. So we said we have 1, 2, 1, 2, and a 0. And what we've discovered is every time we try to do something here, right, I got 2 that shoot into the, regardless of whether I go positive or negative feedback, I've got 2 that shoot into the right half plane, and that's that. Right? So I say, hey, I want to fix this. All right? So let's say I'm going to add my, I know that simple proportional control isn't going to do it. All right? I'm going to say, hey, I know that proportional plus derivative control gets me a 0, and I can move that 0 around. So let me put another 0 here, all right, and see what happens on the root locus. Okay. So I've got 2 that are going. The center of asymptotes moved out that way, all right, and they're now at plus or minus 90. Right. By putting this 0 in, I actually moved the center of asymptotes farther that way. Right? So it went out this way, and I can work out my departure angles, right? And by I've added more phase, right, which decreases my departure angle. So I've got basically one doing this, and then the 2 are going to come in like that and split and go that way. So it was looking good, but it didn't quite do it for me. All right. So that didn't work. No problem. I say, all right, simple PD control is not going to do it for me. So I'm going to say, hey, I'm going to get even more. I'm going to do, shockingly, a second 0 on top of it. All right? And I can do this by gaining 2 PD controllers right on top of each other, actually. Sort of instead of doing, so a PD control looks like a, so this looks like a high-pass filter. So now I'm adding order to my high-pass filter. Right? Okay, let's see what happens now. I've got, this one's on the locus. It's starting to look good. Okay? And I've got 3 zeros, 4 poles, 1 branch going to infinity, and that's that one. Ha. All right? So now all I've got to figure out is my departure angles. And what I'm going to find is 2 of these are going to do something along the lines of that, and the other 2 are going to come out around and do something like that. All right? And what's that? All right. So That was only for a brief moment in case, it stuck around. The interesting thing is there's going to be a gain here. So now I can actually say, hey, wait a minute. I'm going to take a look at my specs, and I'll say, hey, if I'm looking at damping, I need to put, again, the missing piece of information is how fast do these move along their branches, right? Because it may very well be that by the time this pole gets here, this one's already way down here, all right? Maybe. But this is one of those things where, now you start simulating to figure it out. Okay. Also, again, I'm going to note that adding pure zeros is entirely an academic exercise. We don't actually add zeros. We will always add, because this is adding an infinite amount of noise to your system as you get to higher and higher frequency, and we don't like that. We'll get there later. All right. So I can also, by the way, do this same technique with the zero angle and say, all right, well, what do I have to put down to make my zero angle root locus move around? All right. It's not easily as intuitive just because we don't use it as much, but so I had my zero, I had 1, 2, 1, 2, and I said, look, if I put, so my zero angle root locus on this guy wound up being that, that was on the locus, and immediately I say, okay, that's bad. All right, so I know I got to put something else down here to stop this. All right, so the first thing I'm going to do is say, okay, well, what happens if I'm going to put another zero here. Has this helped me? Is it? Zero angle? Or remember, to the left of an even and zero is even. Right? So there's always going to be a branch out here. All right? I'm getting shockingly going to have to do this unless I can get it where there are no branches. Right? And even then, there's still a branch out there. Okay? What does that branch mean? I'm going to give you guys this was the quals question I got, by the way. Okay? You have this system. Okay? It's not a very complicated system, but there it is. All right? So, what are the limits of gain of stability, both positive and negative, on this? Okay? So, you say, well, wait a minute. Okay? Negative feedback, I'm good. Okay? 0 to infinity. So, under normal, where this is a minus and that's a plus, all right, then the limits are 0 to infinity inclusive are stable. Okay? I'm happy. But this is quals. All right? So they say, okay, great. Now what you going to do? All right? And you say, well, no problem. I'm going to draw my zero angle root locus, and that's on the locus, and that's on the locus. But I only have one pole. Only one pole can move. I know it starts off going this way because it goes from the pole and it comes around to the zero. And I say, okay. At what gain does it go from negative infinity to positive infinity? At what point do you reach the edge of the world and wrap around and come back on the other side and go from as fast and stable as you could possibly be to as unstable as you could possibly be? All right? And it turns out that it's not actually that hard to calculate. But this is what happens. This pole is going off here and coming back this way. And there's a gain at which, quite literally, it goes from being stable to being completely unstable. All right? And yes, it goes off the edge of the cliff and it reappears on the other side. All right? Then it's annoying as hell. You're like, wait a minute. So when we go back and we try to stabilize the system that looks like this, where it has 1, 2, 1, 2, and this one, and I say, okay, I'm going to put another 0 down, all right, for the positive angle, All right. One of these roots is actually going to snap around this way and come back eventually. Right. So I think I'm going to have to put the same triple. Right. In which case, let's see, to the, have I changed anything on the, yeah, this one's gone. Okay. So this one's actually bad. Right. So for zero angle root locus, this one's not going to help. Right. But I might wind up doing something like that. Right. So there, nothing, and then I've got, oops, something coming in here, and you start calculating all out your departure angles and your asymptotes and figure out whether you get things to come inside or not. Right. Zero angle in general is a little dangerous. All right. Okay. So now let's go into compensation. All right. And what we know how to do, and now what we're going to start doing. So, compensation. Now, by the way, unless I'm feeling exceptionally evil, I won't ask you zero angle on the midterm. So it'll. You wanted this one where I have 1 and I put 1, 2 here.
No, just when you had the 1 that you added.
Okay, there's the 1.
Just locus should only start at 0. It should be 0 in the first 0.
No, the real axis is going to be anywhere for the zero angle, all of this.
But you've got an odd number between that first 0 and...
Right, it's to the left of any even number is on the locus, right? So basically, 2 of these are going to split and come down. One's going to go in, one's going to go out, and 2 of these are going to split and come down. One's going to go in, one's going to go out. Okay. By the way, this also means that you can gain stabilize. So remember this one? Okay. You can go the other way too, which is you can say, hey, I want to be exceptionally sneaky. All right. Let's. So you say, all right. Here is my system.
But what that demonstrates is right of an odd number is not the same as left of an even number.
It is if left of an even number of 0 is even. Right? If you remember, all the way back here, 0 is even. All right? So left of a 0 is still on the locus. All right? So you're looking, I like this one best, the not left of an odd number is the one that's most intuitive to me. Right? Because I know how to do the 181 so fast, I sort of sketch it up, but then I just, okay, where it is, it isn't, where it wasn't, it is. That's it. Right? I just invert it. Okay, so.
But the right of an odd doesn't fit with left with that.
The right of an odd. Okay. You were the one who told me that one.
Yeah.
That's why I get to listening to an undergrad. All right. Okay, so this one.
At least I figured out that it was
That's true. All right, here we go. So on this one, regular, plain vanilla, 180 degree root locus. I say, here we go. All right, I can find my spot at which I go stable. All right, life is happy. Okay, and again, they say, great, very nice. Except, how fast can you ever make the system move? What's your limit on omega n? 0, right? That's it. That pole's going to that 0, and it's going to slow down and creep in there as I crank the gain higher and higher and higher. All right. And by the way, having a 0 right next to that pole means in the output of the system, it's just going to attenuate the hell out of it. Right. Basically, this system is going to flatline. All right. Where I have to put in huge amounts of preamplifier to get it to actually move anywhere. And you say, but I want it faster. I want to go faster than this. Right. How do I do it? what happens if I do, instead of the 180 degree, if I do the 0 degree, right? The locus is, it's going to snap around. Yeah, just like the other one went off at negative infinity and came back around at positive infinity, this one's going to do the same thing.
How do you calculate that?
You do it with Roth. And it'll snap back around and come on. I mean, if you want to see it, so let's just make it, this is +1 and -1. All right? So that's s plus 1 over s minus 1. All right? So there's g of s. All right? So delta closed loop is equal to, we're going to do this as 1 minus k times s plus 1 over s minus 1, right? Right, so here's the, right, 1 over 1 minus, right, or I guess it's s plus 1 over s minus 1, right, divided by 1 minus that. So delta closed loop is equal to s minus 1 minus ks minus k, right, is equal to s times 1 minus k plus k plus 1, right? And then divide through, and I say this is s plus k plus 1 over k minus 1. Right? So basically, I need to figure out, so what's the gain at which it snaps around from plus infinity to minus infinity? Right? I can just do that. This has to be positive.
That should be S minus that, by the way.
That should be s what?
Minus that quantity.
Minus this quantity?
Yeah. Minus that quantity and therefore minus the
Okay. So there it is. So k plus 1 divided by k minus 1 has to be less than 0 for me to achieve stability. K has to be less than 1. Right? So there it is. So this snaps around the other side of k equals 1. Ta-da. I won't ask you cruel ones like that. Those are strictly reserved for quals. Here's an interesting one. I didn't do this one for you guys, but I should do this one. Okay. One last one, and then we'll start. Then we'll hit compensators. All right. So I've got 1, 2, 1, 2. All right. So here's my system. All right. So for the 180, I got nothing on the real axis. Right. Center of asymptotes is the center right there. I've got 45 degrees each way. All right. Departure angles. Okay. These guys are going to come, meet in the middle. They're going to meet in the middle. They're going to split that way. We now know exactly how to solve for this to find out where exactly they split. All right. This one's going to be a reasonably easy one to do, except that you're going to get two complex answers. The way I would solve this, if this ever came up on an exam, is move those to the j omega axis, resolve it that way, and then I'm just looking for the pure imaginary, and then move it back. Right. So that's that. Now let's do the zero angle. Okay. So the zero angle, this whole thing is on the locus. Right. The asymptotes are there and there. The departure angle is that one goes that way, that one goes that way, this one goes this way, this one goes this way. All right. So, there you have it. Another one. Okay. Enough of that. Compensators. So here's my D of S, my compensator that I get to design, my plant. I got my Y on my output, R, epsilon, let's say I have some disturbance, And I'm just going to hook it back this. Okay. So I had proportional control. Is just a gain K. Okay, you know how to do that. Everyone's happy. I had my derivative control. Wound up putting a 0 right at the origin. All right. So this is KD times S. Okay. And I have my integral control. Winds up putting a pole right at the origin. Okay. So now, if I look at my proportional plus derivative control, what we did there was we said we had a KP plus a KDS, which I rewrote as a KD times an S plus KP over KD. All right. And what that looks like is that, I guess I'll leave it in red, is I have a 0 that I can slide around. All right. So effectively, this gives me, no freedom of choice, not much freedom of choice, no freedom of choice, no freedom of choice. All of a sudden, I put two of them together and I say, hey, I can move this 0 back and forth, and then I've got gain that I can manipulate, right? The gain I manipulate differently from where I manipulate the position of the 0. Okay? And if I do proportional plus integral control, plus integral control, all right, then I have here that I've got Kp plus Ki over S, right, which I can rewrite as Kp times S plus Ki over Kp all over S, which if I look, this one says, hey, I put a 0 here. Oops, rather, no 0. I put a pole here and a 0 that I can slide around. All right. So I'm starting to build up my different types of control, and there are two in particular that are going to be very useful in your life. One is called a lead compensator. And a lead compensator looks like K S plus A over S plus B. Okay. And what that is a 0 and a pole. Okay, so the 0 is closer to the origin than the pole. This is a lead. The other one is going to be a lag. A lag also looks suspiciously, so this is B is greater than A. Right? So the lag is going to be also K S plus B over S plus A, right? Which looks like a pole and a 0. Now, the way to think about this is a lead compensator is a quasi-derivative control. All right? In that, you're getting a 0 that you move around. That looks like pure derivative control. But this pole out here, what it does is it rolls off the response at high frequency. So this is where you say, hey, I'm going to put in my compensation, and then I'm going to band limit it so that it doesn't keep amplifying noise as I get to higher and higher frequencies. Now, the place where this is really interesting, so let's say I have, I'm just going to put a sine wave, A cosine omega t, into my plant. So if I have A over S plus A, okay, then the output here, right, is going to be an A times the magnitude of this guy at j omega plus cosine omega t plus phi, where this is the angle of the plant at S equals j omega, and this is the magnitude of the plant at S equals j omega. All right? So far, you guys with me, right? Yeah? So for A over S plus A, and the reason I'm doing an A over S plus A as opposed to 1 over S plus A is what is the DC gain of A over S plus A? A over S plus A, DC gain. A over A is 1, right? It's got a unity DC gain, right? So whereas if I didn't have the A in the numerator, it'd be 1 over A, and so this would attenuate things, right? So this is a filter, all right, that has a DC gain of 1, all right? All that says is, hey, at DC, this thing passes 1. So let's take a look at what this does as I put in S equals j omega. So I have A over j omega plus A. All right? So at very low frequency, this equals 1. At very high frequencies, this equals 0. At omega equals A, this equals what? Minus 3 dB down, right? It's 0.707, right? This is the 3 dB down point. What's the phase? Here, the phase is 0 degrees. Here, the phase is minus 90 degrees, right? And here, the phase is minus 45 degrees. Right? What I'm doing is, so here is my omega. Here is my magnitude. Starts at 1, there's A, and then it rolls off at 20 dB per decade. Right? So a pole at A, all right, is nothing more than a low-pass filter, a single-pole low-pass filter. All right, and that's all we have time for today. We'll do other ones. Just remember, this is a low pass. So this is a low pass. All right. Likewise, a 0 there is a high pass filter, and we're going to do something really cool, which is I'm going to say, hey, I want the locus to go through this. Just let me just motivate this in the last minute I have. Say I've got, I don't know, I've got something here, and here. Okay, here's my current. Actually, let me just do this. All right, here's my system. Okay, and I know that I put feedback on it, it's going to do that. Okay, and I say, but you know what? I want it to go through that point. Exactly. I want it here. Okay? What I'm going to wind up doing is I'm going to say, hey, this is no problem for me now. I'm going to calculate the phase of this point. Okay? And it's not going to be 180. How do I know it's not going to be 180? Because if it was 180, it would be on the locus already. Right? It's not. I'm going to say, okay, how much phase contribution do I need to bring this point to 180? And say I need 35 more degrees to get me to 180. Okay? I'm going to say, okay, I need 35 degrees of lead to put in there. I'm going to put a compensator that looks like it's going to be a lead. So there's a lead, and that internal angle is going to be 35 degrees. And what that's going to do is, I know that this point is now going to be on the locus. The other things there are going to be other points. We're going to change the locus around. But I know that that point now must be on the locus. All right? And therefore, I can take my locus and I can bend it around. All right? And in fact, if you look at this one's going to go there. These two are still on. Right? So what's going to wind up happening is that it's going to bend this around to do something like that. Right? And I'm going to say, hey, I wanted that point. I now have that point. Exactly. All right? So we'll play with this on Tuesday.
Timing error. Mark. Hi, Mark. Going okay.
All right. Yeah, let me stop that.